Okay, folks, let's go on to the muon. What is the muon?
Yeah, now let's go on to the muon after killing everyone.
Okay, here's the muon. You always want to see what a muon looks like. Here it is, folks. Okay, take a look. Good look. Take a snapshot if you want. There it is.
How long do you spend on that picture, boss?
Well, not supposed to be. I guess that's not the muon that I had in mind. No, I think this is the muon. Okay, it looks something like that. The quantum muon.
Ooh,
It's that little m there at the bottom. Okay, the letter mu. That's what's called a muon. And as you can see, it doesn't look like a particle. It looks like a trace. So the muon is a trace. I mean, what is this thing called a muon?
Yeah, what is a muon?
You know, I mean, I thought muon was supposed to be a particle.
Is that
So, well, let's find out. I looked it up, find out what is a muon. I mean,
Is it
I
like
heard that it's
gluon
something.
and all these things?
Well, it's not the cow that says muon. You know, it's not the little tray. So, what is a muon? And you look it up, and okay, and here it is, the definition of what a muon is. Okay, it says muon, an elementary particle. Okay, similar to the electron with an electric charge of blah blah blah, and a spin of half, but with a much greater mass. So all it is a heavy electron. Okay. It is classified as a lepton. Okay? As with other leptons, the muon is not thought to be composed of any simpler particles. That is, it is a fundamental particle.
There's that fundamental particle until
so
they break it apart, and then you find.
Yeah, this is crazy because they say it's an elementary particle, a fundamental particle. In both cases, it means that it's not made of anything simpler. It doesn't have components. And then they talk about breaking it up and creating neutrons, neutrinos with it, you know, and electrons. And it says muon is an unstable subatomic particle with a mean lifetime of 2.2 microseconds. Okay, so it lasts very little, 2.2 microseconds.
Just long enough for them to get their calculation out.
More or less.
We don't need it anymore.
But this is the issue. The issue is they say it's a particle. Okay, so now we know what it is. Some kind of particle. It's going to be on the standard model. But then you look up and you find this in there, this fellow, and his name is David Tong. He's a physicist or mathematical physicist, right? And he says something different. He says, and we talked about this in the past, recent past, so it's kind of brushing up on what we talked about a little while ago. It says, the best theories we have is that the fundamental building blocks of nature are not particles. Are not particles. I thought the muon was a particle. Now you're just saying that the fundamental. Well, this is a fundamental particle, right? So you're saying they're not particles. So okay, so what are they? But something much more nebulous and abstract. The fundamental building blocks of nature are fluid-like substances. Fluid-like substances. I guess molasses, which are spread throughout the entire universe. So we have this particle that is not really a particle. It's some kind of nebulous abstract substance which is spread throughout the entire universe and ripple in strange and interesting ways. These fluid-like substances we have a name for. We call them fields. So he's saying this muon is not really a particle because we're talking about elementary particles. He's saying, well, elementary particles, fundamental particles, are not really particles, you know, like a corpuscle, you know, it's like a little dot there. No, it's some kind of thing, that substance that is spread out throughout the whole universe. So it's kind of weird because it's very hard to imagine a little particle that is also at the same time spread out throughout the universe. What are you talking about?
It's a really big particle.
Yeah, the biggest particle you ever saw.
We're in a big particle.
And here you see, he
God,
continues.
this thing again.
He says, if you're a physicist, you have a very different picture in your mind when you think about fields. And I'll tell you the general definition of a field. Okay, what is it? It's something, okay, something, right, that is spread everywhere throughout the universe. Okay, so they like the field. Why? Because it's spread out, and they're going to explain or try to explain with this word field action at a distance. That's what they cannot explain. They cannot explain pull specifically, the force of pull. And so the field comes in handy when the particle fails. They cannot, with a discrete particle, explain pull or action at a distance. That's the issue. And he says it's something that takes a particular value at every point in space. So we have values at each point in space, which doesn't concern us. That's a mathematical description. It has nothing to do with what a field is, if it's a what at all. Okay, we're talking about what's. What is a what? A what is an object, a thing. And we're not talking about things so far. They're talking about values. What's more, that value can change in time. Again, they're talking about math here, not physics. So a good picture to have in your mind is a fluid which ripples and sways throughout the universe. And there you have a picture of what they think is vacuum. They say the vacuum, when they remove everything from the vacuum, you still have whatever that nonsense is there. They say those are fields. whatever field is, because again, I see only discrete things in there, and they're saying that the field is like something which is continuous all the way to the edge of space-time. That's not what they're illustrating there, but they illustrate these, looks like particles appearing from the void, and they're saying these are fields. Okay, so we have a problem because what they illustrate does not match what they're saying. In fact, I doubt very much anyone can illustrate a field because there are different notions of what a field is, and it's all ad hoc. When they need the field for this, they'll put all these little particles, and they say they pop in from the void, and they vibrate. And when you say, well, how does it affect that thing over there? Well, it's continuous. It reaches all the way, stretches all the way to there, like an ocean.
Well, where else do you need it? You need it over there, it stretches there too.
And again, the notion that they're giving you is that you have this ocean, and you have the waves. Okay, and the waves are the local vibrations of the ocean. So the local vibration is the particle, and the ocean is the field. One problem with that is that that's a two-dimensional picture, notion or visualization, because you're talking about what's happening on the surface. That's a wave. And our universe is at least 3D as far as the eye can see. And so you would think that, how do you wave something within the ocean? What is it, a current? What is this? So
That's true.
it's a surrealistic vision that these people have. Okay. Anyways, here's the formal definition of field. Okay, shown this in the past, and I'm not going to go through all this again, but it's a quantity. Okay, it's a number that has a value for each point in space and time. Okay, so he's right. It's a mathematical concept, this thing called field. So we start off on the wrong foot because we're supposed to find out what a field is, like a thing, and it's not a thing. It's a mathematical concept, an abstract mathematical concept. And that's what underlies the muon, which is supposed to be an elementary particle, which is a field. So you can see where this is going. We start out on the wrong foot, okay, because the muon turns out to be some kind of vibrating field, which is a bunch of vibrating values. Okay, so far so good? Catching up? Okay.
The definitions.
Yeah, well, no definition at all.
Yeah.
What they did is avoid the definition. In fact, you're not supposed to define if a muon is a thing, you're supposed to point to it. Like you point to a table and say, that's a thing. What do you call it? I call this thing a table, and that one a stone, and that one a tree. Then we can all understand. So you have to point and say muon. That's not what they do. They say, look, it's a field, and what is a field? Well, it's a bunch of numbers, and they vibrate, and they stretch all the way to the edge of space-time. That's an explanation. We don't need a definition. We need for them to point to the muon. Okay, so here this fellow again continues, and he says, you take these two magnets and you move them together. As they get closer and closer, there's this force that you can feel building up, that the pressure that pushes against these two magnets. It's just a little bit magical. This was Faraday's genius. It was to appreciate that even though you can't see anything in between, the space between these magnets will seem to be empty. He said, nonetheless, there's something real and physical there. Okay, so a field is something in there, not the field itself, but something in there, inside the field, is physical and real, which is invisible, responsible for the force. He called them lines of force. In other words, a field is made of lines of force. It's not the field which is the object, it's the line of force which he's saying is the object. We now call it the magnetic field, meaning all the lines of force form a magnetic field. What we need to identify is the line of force. What is this line of force? Not the field. Field is a bunch of lines of force. What he envisaged was that, threaded everywhere throughout space were these invisible objects.
I've heard that one before.
Sounds like the rope model there, threaded everywhere throughout space were these invisible objects. That comes out of a so-called mathematical physicist. Yeah, you have to have objects in there. You have to have things that are threaded throughout the universe and connect things. That's what the notion that they want to give you with field. Okay, but then when you ask them, well, what really is a field? It's a bunch of numbers. Well, that's not what you just said. You said that everything is threaded throughout, and it's the threaded throughout being objects, right?
Of force.
That's what a field is. All the things that comprise the field, which are the threaded throughout. Okay, and so you need physical objects to do physics, and for that you absolutely need to illustrate the object that you're referring to. Okay, and Faraday and Maxwell both said it. Here it is. Faraday said, I cannot conceive curved lines of force without conditions of a physical existence in that intermediate space. And Maxwell said more or less the same thing. He defined it in his book, Field, the space in the neighborhood of the electric and magnetic bodies. In that space there is matter in motion. Matter in motion. That's what a field is. A field is not a thing. It's a concept. It's a dynamic concept made of matter which is in motion. What you have to identify is what is that matter? What does it look like? What do we have there? What is that invisible region there that has this, object that's moving around inside the field? That's what you got to identify. Until you do that, you're not doing physics. You're doing math, maybe. Okay, so here's the muon. And fellow synthesizes, he says, cosmic rays made up mostly of protons collide with molecules of Earth's atmosphere, creating muons. That's the origin. That's the birth of the muon. Okay, there's a collision between cosmic rays, which are primarily protons. They collide against something, okay? Could be the atmosphere of Earth. And now they're going to create this thing called muon, which allegedly is an elementary or fundamental particle, which is a field, which is who knows what. Okay? Stationary muons have a mean lifetime of 2.2 microseconds. Stationary muon could take about 34 microseconds to fall distance 10 kilometers from Earth's surface if they're traveling close to the speed of light. Okay, so you would have 34 microseconds again, maybe 17 times as much as the stationary muon. Okay, so this one's traveling. It reaches the Earth if it can live 34 microseconds. But they say, well, the average lifetime of a muon is 2.2, so there's no way it would arrive at the Earth's surface. Yet many muons reach the ground. They do reach the ground. That means that they apparently are living more than 2.2 microseconds. They have to live at least 34 microseconds if they want to reach the ground. So how is this possible? There seems to be a contradiction there. Time dilation, muon lifetime larger for an observer on Earth. That's what's happening. What's happening is they bring time dilation, special relativity, to explain why the muon survives all the way to the Earth, despite the fact that it only lives 2.2 microseconds instead of the 34 that it would need to reach Earth.
What does the observer on Earth have to do with the... Either the muon lived 2.2 microseconds, or it hit the ground.
Well, here it is.
They're mutually exclusive no matter what you do.
You would think, and that's what I'm going to show right now. But let's get to this point. Rather than question the idiocy of quantum mechanics, the mathematician used the muon as proof of special relativity. Okay, so instead of saying, look, there's something wrong, we need to erase the board and start all over, they said, no, we have a solution.
Ta-da!
The solution is that if we bring special relativity in, we can explain why the muon reaches all the way to the Earth, despite the fact that it would be required that it lives 17 times more than it usually lives. This is the problem. We have a problem there, and they solved it with special relativity.
It lengthened time for itself just to hit the ground.
Yeah. Okay, so here's the description out of the Wikipedia. Although their lifetime without relativistic effects would allow a half survival distance of only 456 meters, the time dilation effect of special relativity, from the viewpoint of the Earth, meaning the observer, right, allows cosmic ray secondary muons to survive the flight all the way to the Earth's surface. Since in the Earth's frame, the muons have a longer half-life due to their velocity. From the viewpoint of the muon, now we have the muon, he's going to be thinking, he's going to be analyzing himself, okay? The muon, on the other hand, it is the length contraction effect of special relativity which allows this penetration. Since the muon frame, its lifetime is unaffected, but like it says there, length contraction causes distances through the atmosphere and Earth to be far shorter than these distances in the Earth's rest frame.
So we see it as thousands of kilometers, and it sees it as only 400 meters.
Exactly. The muon has a short...
So we see it is traveling a bunch of kilometers.
The muon is short-sighted.
And the muon says, no, it's only 300 meters. What you talking about?
Yeah.
The distance for it is shortened, but not for us.
And that comes out of Einstein's relativity, which says that when you're traveling at the speed of light, what you see in your frame of reference is different than what the observer from far away sees. For you, everything is normal. You look around yourself, everything is normal, everything's stationary, more or less. The tear is there and everything. But if the Earth is flying at the speed of light, right, the person far away will see you a little different, or will time you a little different than what you're timing things happening around you. That's more or less the idea behind the muon. And so here we have one MIT mathematical physicist, and he gives us an example. He says, lifetime, again, 2 microseconds, right? If the particle were moving at nearly the speed of light, it could only move about 600 meters. How can a particle that is produced 20 kilometers above the Earth reach the ground if it decays in 2 microseconds? Special relativity saves the day. Suppose the muon is moving at 99.99% of the speed of light. As seen on the surface of the Earth, time dilation stretches out its lifetime to, makes the calculation, comes out to 140 microseconds. With this lifetime, the muon can travel a distance of 42 kilometers before decaying. The muon can easily make it from high up in the atmosphere to the ground. Okay, this was published by the MIT people. Okay. So there you have the example. Muon is essentially a particle of distance traveled, as I say. And for this, we need to distinguish between distance and distance traveled. Those two have nothing, one has nothing to do with the other. Okay, they're comparing apples and oranges, the mathematicians as always. Okay, so here you have a muon. Okay, it's going to go in a straight line all the way to the Earth. Okay.
Yeah.
So they say the muon shouldn't be doing that because it only lasts 2.2 microseconds, and it would take at least 17 times as much if it travels close to the speed of light to reach the Earth. Okay, so what happens? What we're looking at is the locations. Okay, what you just stared at was a movie, a film of the muon falling, and if we chop that up into all the frames, right? Each location that it has with respect to the Earth, right? Then you would have something like this. You would have different locations of the muons. Okay, you would just partition it into frames or locations. In this case, frames and location, frames of the movie and locations, you could say, are the same thing. Okay, so what is the issue here? Okay, why don't we have the muon so that we can distinguish between distance and distance travel? Let's have the muon travel only halfway. Okay, so here goes. Muon only travels halfway. Now we're going to look at that situation there. Okay, and here we have it. There it is. You have the, on the one hand, you have all the frames in the film of the distance that it traveled, and on the other, you're going to have the distance that it still has not traveled. Okay, so one is a movie, and the other one is like a photograph. It's a static image of a separation. Okay, from the muon where it ended up last to the Earth's surface. And here you have, we label this so that you know what we're talking about here. One is distance traveled and the other one is distance. Distance is just separation, whereas distance traveled is, again, all the locations that the muon had on its trip to halfway from its starting point to the surface of the Earth, okay? And we label that one more time just to make sure. One is a movie and the other one is a picture, okay? Yeah. So that we understand exactly what, hopefully everybody understands what we're talking about here. We're saying that one is distance traveled, the other one is distance separation. Okay, one is a movie and the other one is a picture,
even
a photograph.
Wrong. Photograph also is wrong because it's more like a mental.
Well, it's a static.
Right?
It's a static. What I'm saying is distance is a static concept, whereas distance traveled is not.
Yeah.
Distance traveled is motion. Distance is, it's just a separation.
Yeah.
Okay, that's what I'm trying to say here. Okay, so we got that, at least the notions. What's the problem? Well, first thing we have to do is define words so that we know what we're talking about. Let's define them, okay? We say that an object is that which has shape. Distance is the separation between objects, okay? We have two objects there, two blue boxes, and this is just a region between them that has no matter. Location is the set of distances, one object with respect to all other objects in the universe, and distance traveled, something totally different. We call it motion, displacement, you can call it if you want. Two or more locations of an object. That's a dynamic concept. Okay, so these are all different notions, different concepts. And so we need to understand the differences between them. Okay, so what's the issue? When the forefathers, people like Lorentz and Poincaré and so on, they came up with this length contraction, as they call it. They were actually comparing apples and oranges because length is not distance. Okay, length has to do with what an object measures and not with the separation between two objects, which is what distance is.
So we have length, distance, and then distance travel.
And distance travel is something totally different because it's what one object traveled. It has nothing to do with separation.
Did you say distance is the length of space? That's a weird way to put it, but
yeah, but length should be reserved for objects, for things. That's where the problem is. Okay, so they use this, but look at this. The issue is that velocity there is distance traveled and not distance. And today everybody uses the word distance when it's not distance. It's very confusing because people think that they're talking about separation and they're not. They're talking about a movie. They're talking about a little ball that is at different locations. That's what velocity has to do with, and not with separation between two objects. Okay, so that's the first thing I want to point out. Okay, and here we have my versions to show you the difference. Distance is what lies between lengths.
Yeah.
That's a way we like to synthesize that. Length is what an object has. A table has length. Between two tables, what we have is distance. Okay.
Essentially, it's like what I said. Distance is the length an object would have if it were in between those two.
Yeah, but see, the issue here is that the mathematicians, whether they're going to measure a table or whether they're going to measure between two tables, they have to unroll the measuring tape. And what they're doing in all these cases is measuring or counting how many units of that measuring tape either the table has or between two tables. In other words, for them, it's all the same. They're going to talk about meters, and what they're doing is counting the number of meters between two tables, or one edge of the table to the other edge of the table, or the amount of time you ran.
Right.
All that for them is the same. It doesn't matter. So it's like the issue with dimensions and coordinates and vectors. For them, it's all the same because they're not talking about dimensions, coordinates, or vectors. What they're talking about is number lines. And here they commit the same crime.
But how is that relevant?
Okay, let's show why it's relevant. Here it is. Okay. Here we have location, location, location. This is what I want you to pay attention to. Here we have the universal movie. Okay. Universal movie, every frame is a location. Now you can chop that up as much as you want. You can say that every frame just represents 1/gazillionth of a gazillionth of a second. It doesn't matter really. You can also say that's just 1 second. The important thing here is that you see the green dot there that's moving around. It has location with respect to every atom in the universe. Okay, that's what the red arrows are showing. So, but there has to be a correlation between the universal movie, every matter in the universe, and the local movement of the muon. Okay, the local movement of the muon is a movie also. And there has to be correlation because the local movie of the muon is a component of the universal movie. So there better be a one-to-one relation. Yeah. This is not the case in mathematical physics.
What you're saying is time moves everything at the same time.
Yeah, if
not a little faster for this guy and a little slower for that guy. This guy, everyone's speed has to be this.
Well,
everyone's time has to be the same.
This is the way I put it. What we look at here is the following. Let me put this down here so we can. What we have is the following. You have God. You know, God is all powerful. If you don't like God, you pray to the devil. Okay, let's put the devil in there. Okay, the devil stops the universe. There's nothing moving.
Yeah.
No electron is moving. No atom is moving. Nothing is moving. He froze the entire universe, all the matter in the universe. That's a cross section of time.
Okay.
So that cross section of time is or cross section of motion, location. That's all we have. In that frame of the movie, all we have is location. The next one, the next frame is also location, just location. So we have motion built from all these locations because motion is two or more locations of an object.
Okay.
Okay. There has to be a correlation locally to the rest of the universe.
Yeah.
Okay. So if a muon is moving here in this region originally, right, we don't care because the location of that muon at any point in time has to correlate to the rest of the universe. It's got to have a distance to every object in the universe.
Yeah.
That's my point. Okay. And so here we see, let's put it back. Here we see that according to mathematics, that those 10 frames that you see there, they only form a small portion, less than 1 second of the universal movie. The universal movie is every object and the distance from every atom in the universe to every other atom in the universe. That includes every muon in the universe.
Yeah.
Okay? And what these people are saying is the muon lived or thinks it traveled only less than 1 second, meaning it got rid of a lot of frames, or it's missing some of the frames of the universal movie. Somehow these people made the movie, some of the frames in the movie, some of the locations disappear.
Yeah.
Because there's no other way that you can say that for the muon, it was less than a second, but for the universal movie, the whole thing lasted more than 1 second.
So you're saying Father Time has to audit the muon?
Well,
hey, buddy, you're missing some frames here.
What I'm saying essentially is, you can't have it both ways.
Yeah.
Math is one thing. They can do all the calculations they want. They can take Lorentz contraction and do whatever they want, play around with the numbers. That's fine. They can do whatever they want there. But when they come to physics, the muon has to have location. Okay? That's a qualitative notion. Yeah. It has to have distance with respect to every atom in the universe. Yeah. And if you say, look, locally, what happened to the muon, it did this very fast, below 1 second. At the same time that for the rest of the universe, it was more than 1 second. Okay? Let's just put it in those terms. Yeah. You can't have that because location has to be for every frame of the movie. Yeah. And these people are saying, look, we got rid of some of the frames, some of the locations.
But only in one of the movies.
Locally.
Yeah, like what?
So one of the two, someone's missing or someone's putting too many frames of the movie, depending on what side you're looking at from with the context. There has to be location per frame, one location per frame for every, you have to count for every location of the muon in every frame of the movie.
Essentially what you're saying is 1 second passes the same for everything. The best way to put it, like, is kind of how you define a year, the Earth going around the sun once. Assuming we made this really slow, right? How many times did let's say a muon lasts 1 year for itself and 2 years for everyone else, right? did the Earth go once or twice around the sun?
Yeah.
By the time it hit the Earth.
And all we have to do is go to the file cabinet, the devil's file cabinet, open it up, and find out what was the location on that file. And we pulled it up, and that's a single frame of the movie. It has only location. The muon had better be in there. Okay, in every frame I should see the muon. And these people are saying, no, we got rid of some of them only locally for the muon, but the rest of the movie, Universal movie, is okay.
But isn't that a general problem with special relativity?
Yeah,
it's just a general problem because that is essentially what they're saying. They're saying for some things time goes faster, for some things it goes slower.
Yeah, that's okay in math. You can do all the calculations you want, but we're talking about qualitative location.
How many frames were
every object in the universe had better have location?
How many seconds passed? If 2 microseconds, or what was it?
Yeah, 2 microseconds.
If 2 microseconds passed, right, is the muon dead or did it hit the ground? We don't care about the rest of it. Where is the muon right now after 2 microseconds?
Look at the file.
No, but essentially that's what you're saying. From the beginning of when the muon started, just start the timer 2 microseconds. Is it dead or did it hit the ground? They're mutually exclusive. It's either dead, so only 2 microseconds pass, or it hit the ground, so the muon lives more than 2 microseconds.
Well, what they try to get around that, saying that what the muon experience is different than what you experience as the observer. And I'm saying we don't care what people observe, what they calculate. We don't care about any of that. There has to be one location per frame in the universal movie. And the muon had better be in each one of those frames. And you cannot say, well, for the muon there were 10 frames, but for the universe there were 1,000,000 frames. You can't do that. I mean, this is what they're saying. They're eliminating locations of the muon.
That's what I'm saying. We got to audit the muon. Hey, buddy, you're missing some frames.
We got to go to the devil's cabinet and find out what's in there.
Someone's cooking the books over here in the muon.
Anyways, here's the conclusions. Okay. Oh, sorry, wrong one. Let me get rid of this one.
How many frames per second does the universe play in?
Well, you can make it gazillions of a second. I don't care. It doesn't matter to me. Really, you chop it up as much as you want, but there had better be location for every object in the universe. Otherwise, the muon disappeared, or some of the frames disappeared. Okay, so here's the conclusion. Muon is supposedly a particle, but a particle is a field, and a field is many values.
What's with the sad smiley?
Well, you'll see it. Why? So this implies that the muon is a concept. It's not an object. It's not a thing. Okay? Muon is a concept because it's just the many values, which is a mathematical concept. Muon, even worse, it's a dynamic concept. Why? Because it's the particle, quotations on that, of distance traveled. Muon only has importance in the discussion of distance travel, okay? Because they want to show you that, the muon went faster than what you're supposed to think about the muon, and the way they explain it through special relativity, saying, well, for the muon, it was a shorter distance. Okay.
Can we really quick talk about why they even invented the muon?
Well, let me finish this and we'll do that. They depict it as a trace, okay? And the muon is, again, distance traveled. It should have one-to-one correspondence or relation between frames of the movie, of the universal movie, which each frame represents a location only, which is the set of distances to every atom in the universe, every living thing, or every piece of matter in the universe, okay? Anything that exists. That's for the universal movie. And what they're doing is they're either missing or they have surplus frames, depending on the context, from which angle you're looking at it.
The muon's missing or we're adding too many.
Right. And so the muon has nothing to do with science, and that's why he's got a smiley face. I'm sorry, a sad face. The smiley is no longer smiling. Why? Because the muon is not part of science.
Rest in peace, muon.
Okay, so the issue is the following. The way they detect this. That's what you got to look at. Again, you have cosmic rays, which are protons. They collide, essentially. They collide against the atmosphere or whatever, doesn't matter. And when they collide, they break up, okay? And the muon travels to Earth, okay? It travels to Earth, but if it's a stationary muon, one that's just floating out there, the average lifespan is 2.2 microseconds. When they're traveling to Earth, they should be... it should take them a little more than 2.2 microseconds, okay, whatever the calculation is, not important. Yeah. But the point is, it's got to have a longer lifetime. Yeah. And what they realize is that somehow they detect them at ground level. Yeah. They were able to detect muons at ground level. They say, how can this possibly be? The muon should have died by now. Yeah. Turns out he didn't die. He went all the way down there. And instead of rejecting the whole nonsense of muons, what they said is, let's explain it with special relativity. And special relativity says, length contraction. Distance contraction. The two mountains move closer to each other because the muon travels between them. You know,
this nonsense stacked on nonsense.
Yeah. That's what they're saying. And I'm saying, hey, no problem with all that. That's math. Now, when you come to physics, show me locations of the muon in every right. I want to see the muon at every location in every frame of the universal movie.